Welcome to the Data Science Internship Program at Cloud Credits Technologies. In this presentation, I'll be walking you through Project 2, the House Price Estimator, a regression project that aims to predict house prices using machine learning. The main goal of this project was to create a regression model capable of accurately estimating house prices based on a variety of factors. We're talking about things like location, the size of the house, how many bedrooms it has, and the amenities it offers. A key part of this project was also to use data visualization to really understand the distribution of house prices and how different features influence them. The project followed a structured approach, which can be broken down into 10 key steps. First, we defined the problem. Next, we gathered and prepared our data. Then, we moved on to exploratory data analysis, EDA, where we visualized the data to find patterns. After that, we engineered new features, split the data into training and testing sets, selected a suitable model, trained it, evaluated its performance, and finally, we focused on improving it. As an optional step, we also explored deploying the model. To find the best approach, I experimented with a range of regression models. This included linear regression, as a baseline to compare against random forest regressor, great for capturing those complex, nonlinear relationships, gradient boosting regressor, a powerful boosting method for increased accuracy. XGBoost regressor, an optimized version of gradient boosting with built-in regularization. Lasso ridge regression, to handle multilinearity and help with feature selection. The first step was clearly defining the problem. Our objective was to predict house prices based on various features of the houses and their location. It's definitely a regression problem because we're trying to predict a continuous numeric value, the price. We want to build a model that can accurately estimate the price of a house, which is useful for real estate valuation, identifying undervalued or overvalued properties, and just understanding what factors really drive housing prices. Why regression? Just to reiterate, we chose regression because the target variable, house price, is continuous and numeric. We're predicting a number, not a category, so regression is the right tool for the job. To begin, I imported all the necessary Python libraries. These are the toolkits that provide the functions for data manipulation, mathematical operations, visualization, and machine learning. Next, I loaded the house data from a file, usually a CSV. I then displayed the first few rows to get a feel for the data, a sanity check, if you will. I checked the data type of each column, whether it contained numbers, text, or something else. I also calculated basic statistics like the mean, minimum, and maximum for the numerical columns. Finally, I checked for any missing values in the data and planned how to address them. Data pre-processing is essential to clean and transform the data into a usable format. I started by converting the date column into year and month columns. Then, I removed the original ID and date columns since they were no longer needed. To capture how old a house is, I created an age column based on the sale year and built year. Also, I created a renovated column to show whether the house had been renovated or not. Any missing numerical values were filled in using the median value of their respective columns. Finally, I handled any outliers in the square feet living column by capping extreme values at reasonable limits. This is where we start to understand our data through visualizations. Let's walk through each visualization and what we learned. House price distribution. I used a histogram with a kernel density estimate, KD, to see how prices are spread out. The analysis showed the distribution was skewed, meaning most houses are cheaper, with fewer expensive houses. This skewness of price, 4.02, might warrant a log transformation later on to make the data more normally distributed. The mean price was around $540,088. Square footage versus price. A scatter plot revealed the relationship between house size and price. As expected, bigger houses tend to be more expensive. There's a positive correlation of 0.65. Bedrooms versus average price. A bar plot showing average price per number of bedrooms. Noticed an increasing trend up to a point, and some interesting outliers. It might be useful to group bedrooms into categories. Correlation heat map. This is where we visualize relationships between all the features and the price. It confirmed that grade, square foot living, square foot above, and square foot living 15 are the most correlated with price. This highlighted features for further investigation and model building. House prices versus location. Visualizing prices on a map using longitude and latitude showed how prices vary geographically. Average price versus grade. We saw a clear increasing trend in average price as the grade of the house increases. Grade generally refers to the construction quality and design of the house. Year built versus price. This revealed any trends in price related to when a house was built. Interestingly, 1933 had a very expensive average price year. Waterfront versus price. A box plot clearly showed that waterfront properties command significantly higher prices than those without waterfront access. Square footage living area distribution. This showed the distribution of living area size and its skewness, 0.73, indicating that most houses have a smaller square footage. Bathrooms versus price. There was a positive correlation, 0.53, between the number of bathrooms and price. Count of conditions. The distribution of house conditions shows that condition 3 is the most common. Feature engineering is all about creating new features from existing ones to potentially improve our model's performance. First, I reused the aged and renovated features from pre-processing. Then, I created new features by combining existing ones, for example, multiplying square foot living and grade to get an interaction term. I also created polynomial features by squaring some numerical features. And grouped houses into bedroom categories, then converted them to numerical data using one-hot encoding. To keep the model simple and efficient, I performed feature selection using a random forest model to determine the most important predictors of house prices. The analysis indicated that lat, long, and the combined feature square foot living grade were the most important. So those became our features for the model. Now it's time to split the data into two sets, a training set to teach the model, and a testing set to evaluate how well it has learned. A 70/30th split is common. It's important to split the data into stratified bins for even distribution. I used robust scaler to scale the data. Scaling ensures that no single feature dominates the model due to its magnitude. Choose a model. Based on the EDA and the nature of the problem, I chose a gradient boosting regressor. Train the model. To find the best configuration for our gradient boosting regressor, I used random search for hyperparameter optimization. This involves defining a range of values for each hyperparameter and then randomly trying different combinations. After fitting to the training data, the best hyperparameters found were learning rate of 0.0472, loss function of Huber, max depth of 6, min sample leaf of 4, min samples split of 8, number of estimators of 289, and a subsample of 0.86. After training, it's crucial to evaluate the model's performance on unseen data, the test set. I used metrics such as mean squared error, MSE, root mean squared error, RMSE, R squared, R2, and mean absolute error, MAE. The model achieved an R squared of approximately 0.81, meaning it explains about 81% of the variance in house prices. The mean squared error, MSE, was 26,894,623,170.508. The root mean squared error, RMSE, was 163,995.802 and the mean absolute error, MAE, was 77,231.614. Now, let's improve our model's accuracy. First, we're going to create some new features by combining existing ones. Think of it like discovering hidden relationships in the data that the model can learn from. We'll also create ratio features, which can sometimes be more informative than the original numbers. Next, we need to select the most important features so we don't overwhelm the model with irrelevant information. We'll use a technique called recursive feature elimination, or RFE. This method automatically chooses the best features. First, we'll fill in any missing data and make sure all the features are on the same scale. Then, RFE will rank the importance of the features and pick the top ones. Now comes the fine-tuning. We'll use a process called Grid Search CV to find the perfect settings for our gradient boosting regressor model. It tries out different combinations of settings and chooses the ones that give us the best prediction accuracy. Finally, to avoid overfitting, which is when the model learns the training data too well and performs poorly on new data, we'll use a technique called early stopping. We'll monitor the model's performance on a separate validation set during training, and if it stops improving, we'll stop the training process early. After these improvements, we'll evaluate the final model to see how much better it performs. Deploy the model. Now, let's deploy our model so we can start making price predictions. We saved the trained model and the scalar in the training notebook. The model and scalar were saved to model.pkl and scalar.pkl, and then uploaded to the deployment notebook. Setting up. First, we're connecting to Google Drive. This is like plugging a USB drive into your computer. It allows the code to access the files containing your trained model and the scalar, which are stored on your Google Drive. Loading the model and scalar. Now, the code is looking for two specific files, model.pkl and scalar.pkl. These files are located in a folder on your Google Drive. Think of them as the brain of our prediction system, the model, and a special measuring tool, the scalar. The code opens these files, loading the model and the scalar into the computer's memory, ready to use. Just like taking a recipe and measuring cup out of the cupboard. An important step is the error check. If the code can't find these files, or if something goes wrong during loading, it will print an error message and stop the process. The prediction function. The core of our deployment is the predict price function. It receives a set of information about a house, number of bedrooms, square footage, location, and so on. This is the information we'll use to predict the price. Inside the function, first the input data will be prepared. The house information is converted into a table format, like a spreadsheet. The code calculates new features from the existing information, such as the age of the house. Only the columns, features, that were used to train the model are selected, ensuring the data is in the correct format. The scalar tool we loaded earlier is used to adjust the input data. This scaling is vital, as the model was trained using scaled data. Next, the code will feed the prepared data into the model. The model processes the information and predicts a price for the house and returns the price for the house. And don't worry, the code includes error handling. If there's a problem, like missing information, it will print an error message. This last part shows an example of how to use the predict price function. It creates sample data about a house, bedrooms, bathrooms, area, etc. This sample house information will be passed into the predict price function. Finally, the function returns a price, which the code then prints on the screen. If the prediction fails, it displays an error message instead. The code runs with the sample data and returns the result: predicted house price, $689,155.649. Conclusion: this project successfully developed a house price prediction model using regression techniques. Different models were tested, and through feature engineering, selection, and hyperparameter tuning, the model's accuracy was improved. The final model provides reasonably accurate price estimates, as shown by the evaluation metrics. Recommendation: to further enhance the model's performance, future work should focus on exploring more complex features, experimenting with advanced machine learning algorithms, and gathering more comprehensive datasets. Additional data could include economic indicators or neighborhood-specific information. Thank you for watching. I hope this presentation provided a clear overview of my work on the house price estimator project. And stay tuned for more exciting projects.